Okay, if you're a math buff like me, you probably would have seen this one video by Dr. PM and Black Pen Red Pen wherein they discuss about the topology sine curve, and this is what it looks like. So it looks like a normal sine curve, but as we get closer to zero, it gets more and more chaotic, right? Um, and so there's this one part, there's a section of the video wherein it's not explicitly stated that this point over here is the same as this point over here, right? And so they argue about it for a while, and soon Dr. Payne just says they identify those points, right? And we topologists always throw this term around: identify this, identify that. Take a line segment to construct a circle S1 out of it, just identify the endpoints. But what does it mean to actually identify a space? Or what does it actually mean to identify a part of a space? Like say, sometimes we say that to construct a sphere out of a disk. So here's my sphere, and here's my disk. It's a solid, it's a circle with its interior. What we do is identify all the points along the boundary, right? But what does it actually mean to identify? When we topologists say identify, or an identification, we mean one and only one thing, at least most of the time. And what that means is a quotient. Oh, you may be thinking, what does quotients have to do with topology? How does dividing one thing from another have to do with topology? Well, the thing is, quotient in abstract algebra and ultimately in topology is an entirely different thing. It's an entirely different thing. In abstract algebra, it's defined as ignoring some things. And in some sense, it can be traced all the way back to basic arithmetic with dividing and ending up with, something. We ignore sort of the members and then sort of divide it, class it up. And in fact, that notion gets carried on to the quotient group. But in topology, what does it mean to actually identify something? When we identify a space, what we mean is we're taking its quotient space with respect to identifying, or with respect to classifying those set points we're saying to identify as the same. What do I mean by that? Rigorously speaking, well, if X is my topological space, remember from the last video, or from the first video, that each topological space has an associated topology to it. And each of these topologies give me a different space for every time I define them. So every time I have a topology defined on a space, it gives me a different space, no matter what, depending on what my X is. Okay, so rigorously, this notion of a quotient in topology is encapsulated by the quotient topology. And the key word, the key concept for this is an equivalence class. So what is an equivalence class, or an equivalence relation? Well, equivalence relation is a relation between objects that is reflexive, associative, and commutative. So relations, remember relations from functions, is that relations are just a more general form of what a function is. A function is a special case of a relation. And in fact, the equal sign, or the equivalence sign in calculus, is a special case of an equivalence relation. Equivalence relation. So is the homeomorphism, the homotopy, H, and also the homotopy equivalence and the diffeomorphism. So these guys, also the cobordism is technical and equivalence relation. But what I'm saying is equivalence relations it's basically in a relation for two objects on both sides of these things, wherein I can switch them around, and also if I have three objects and I equate one to the other and equate that second one to a third one, immediately the first one is equal to the third one, at least, or at least the relation holds. So this encapsulates, or this concept encapsulates our notion of considering things as the same. Okay, so Alright, so if I have X as my topological space, what is the quotient topology? So as I said in the last video, or in my first video, about topological spaces, the first thing we need to do when constructing a new topology is to construct a basis. So now I will consider every subspace S in X, but notably, it is inside this new space X mod tilde. But don't mind the notation just right now. It's simply notation. So what this means here is a space X with an equivalence relation applied on it. So basically, we're stating a rule for when we consider two elements inside the space to be the same, and then we're considering the space wherein that rule is applied on the space. And then this is what we get, X mod tilde. And so the map Q that takes X and maps it onto X mod tilde is surjective. That's one thing. Surjective. Well, it is surjective because, for one thing, X is less than X mod tilde. Or at least it has a smaller cardinality. It may have a bigger cardinality, but ultimately it would have smaller cardinality. So next, what I want to do is define a new thing, Q to the minus 1 of S. So this is my pre-image of S, which is inside this here. So what does S look like inside X? And we define that to be equal to all X in X in the original space X, such that the equivalence class of X is inside S. So what we're doing with Q here is taking every element in X and sending it to an image Q of X, which is inside X modded out by that equivalence relation. Okay. So next, alright. So if I take everything here, every one of these guys, or every one of these guys as an open set in a new topology, we can form a new basis. Yeah. So every family or every subset U in Y, which is just X mod tilde. So everything here collected into a set forms a basis. Oops, excuse me. Stand. All right. Yeah, I'm using a stand, so excuse me for that one. All right. So this finds the topology, and that is the quotient topology. So this is a basis. So all U in Y, which is X mod tilde, so all U and Y, such that the set of all X in X, such that the equivalence class of X is inside U, is an open set in this new topology. So this over here is my quotient topology, formally speaking. Alright. And so if I pair X mod tilde or Y with this TQ, this is my quotient space. Or this is the quotient space. That's the quotient space. Okay, so let's do an example. Of course, an example already a while ago was this line segment, so running from 0 to 1. If I identify the space, so usually we denote a unit interval from 0 to 1 as I. And this is all real numbers running from 0 to 1, wherein 0 and 1 are also part of that set. And this also has, we can equip it with the standard topology on R, and it wouldn't matter. But alright, so if I quotient I with this relation such that 0 is equivalent to 1, I would get S1, or a space that's homeomorphic to S1. Because notice, when I identify these two things, I'm considering them the same point, essentially. So they become one singular point, and then when I connect it, it becomes a closed space. Right? So originally it had a boundary, but now it doesn't have a boundary, a one-dimensional boundary. Right? It doesn't have a hole now, or it doesn't have, it doesn't have boundaries. It has a hole in the middle, a two-dimensional hole, but right now there is no one-dimensional holes here, so there are no boundaries. This is S1. So likewise over here, what I'm doing along the boundary of D2 is I'm considering them as one singular point, so they sort of become like this, or they at least get mapped onto this one singular point up here, and then it becomes S2. Now, another example would be this square over here, and then I'm gonna draw some arrows indicating which edges get identified. So double arrow, and then singular arrows. This here, when I identify these edges, give me a torus. Why? Because I'm considering every single one of these points as the same, so it'll give me a cylinder first, and then now I have the double arrows here, which are this circle and this circle. So this is a small, so the circle is a small case or a part of this larger identification, wherein this line segment here becomes a circle because I'm identifying this endpoint with this endpoint as I'm identifying these two edges. And same thing with here. But the thing is, we're not quite done yet with the identification because we still need to identify this circle with this circle at the bottom. When we wrap it around, or when I bring it around and then sort of, or bring it inside and then connect those two circles together, because we're considering them as the same circle or one circle, we get a torus. So in summary, that's what we mean by a quotient topology, or at least but what we mean when we say we're identifying 2 points or something in a space. What we mean is we're taking its quotient or its quotient topology. So shorthand for writing that is, alright, so let's say I want to connect two spaces together. So that means I would have to form a quotient topology. So this is X union, sometimes we use a disjoint union, so, and then I have an alpha and then Y, where an alpha is inside either X or Y. So this is what we mean by gluing two spaces together. So what we really mean by this is we're taking the disjoint union, or at least just the general union X and Y, and then we're quotienting out by the relation we're in. We identify the necessary subsets of either of these guys, or subspaces of either of these guys, in order to get a connected singular surface. Originally, we have a disconnected surfaces consisting of X and Y, but once we identify those subsets of X and Y, we would have one path component. So there, this is about quotients.